the introduction, and I should also thank our local organizers for inviting me to here again to give a talk. So actually last year we announced our system in Frankfurt. And also in an invited talk I provided some more technical details about the system. So now 1 year has passed, and we did make some very exciting application results on this machine, trying to solve some extreme scale scientific or engineering problems that we can solve using this supercomputer. So in my talk today, I'd like to share with you actually some of our most recent experience designing and tuning applications on this supercomputer with over 10 million cores. Okay, so first I still want to sort of go over some of the key features of the machine and also some brief discussion. Well, I guess last year when we announced the Sunway TaihuLight, many of you might be like, well, where does this machine come from? Right? What does the name Sunway TaihuLight even mean? So actually last year I spent quite a few slides to explain the meaning of the Chinese characters to you guys. It's actually one of my hobby to teach people about Chinese characters. But anyway, Sunway is actually a family of machines, supercomputers that actually date back to the year of 1998 and even before that. So the first Sunway machine was actually designed with the goal to provide weather forecasting service for a very important parade in the next year, 1999. That was the 50-year birthday for the People's Republic of China. So as you can imagine, it's a very important thing and needs a very important supercomputer to support that. Now, I guess many of you should be very familiar with this blue light machine. It's in Jinan, and it's kind of the truest generation of TaihuLight. And if you look at these two machines, they actually have a lot of similarities. If you have been to both these two centers, if you look at the cabinets, so both computing systems are actually organized as circles. It's kind of very special, right? It's also a design concept that I like. And if you look at the processors, they're also kind of similar. So both of the two processors are organized as 4 core groups. Now the difference is, of course, for blue light, in each core group you only have 4 homogeneous cores. Now for the TaihuLight, it's actually a many-core processor. Each core group has 65 heterogeneous cores. So this shows some more details about this many-core processor with 4 core groups. And actually, one question I received quite a bit last year is like, you know what, this one looks very similar to IBM Cell in the last decade. So what's the real difference? Well, I guess the concept of having different kinds of cores in one processor is of course the same. But if you look at the design details, it's actually quite different, right? So we have these 4 core groups, which is a design style that we inherited from the previous generation. And then if you look into the core group, we have 1 MPE, which is kind of similar to the traditional CPU cores, and the 65 CPEs are actually organized as an 8x8 mesh. So you have row and column buses where you can actually exchange data very efficiently among the 64 CPEs. Okay, so with the CPUs, how you actually get a system with 10 million cores. So this is sort of the math here. With each core group, we have 65 cores. So 4 core groups in 1 CPU, that's 260 cores. And with just this one cabinet, we can have 1,000 CPUs integrated into one cabinet. That's providing a performance of roughly 3 petaflops. And then with 40 cabinets of these, we are having this system with 10 million cores. And this also kind of shows the way that we parallelize the computation on this system. If you look at this 10 million cores, it's actually divided as 2 levels. So for each core group, we usually allocate 1 MPI process. So in the maximum parallelism, you can have up to 160,000 MPI processes that you program. And then within each MPI processes, we still have up to 65 cores that you can use with different threads. Okay, so, and also this is what I did yesterday. I was trying to provide you some more concrete impression about this machine. So I tried to get some of the most important hardware numbers and also these benchmark numbers to kind of compare TaihuLight with some other supercomputers. So as you can see from these two figures, the one on the left is about the hardware features. So the large blue box is Sunway TaihuLight. Our advantages are very clear, right? We have, for computing performance, we have significantly more than these other systems. So as a result, for compute-intensive benchmarks, like dense matrix operations in LINPACK, and also for explicit finite difference or finite element methods in HPGMG, we are getting pretty good results. And actually, our colleagues have just finished the HPGMG results and have just sent them to Eric and his colleagues. And we also have very good sort of performance per cubic meter. As you can imagine, we have sort of 1,000 CPUs in just one cabinet. And also kind of good performance per watt. Last year we were the second. Now this year we have more and more computers coming out with the P100 GPUs. So the ranking does not look that great this year. But still, I should say this is also a good efficiency. Now, of course, we have disadvantages also, clear disadvantages in memory systems. So if you look at this figure, we have actually 10 times more computing power than K computer. But our memory size is sort of similar to K computer. Or I should say slightly less than K computer. And if you look at the memory bandwidth, we are also not very good. We are not providing comparable memory bandwidth sort of relative to our very good computing performance. So as you can imagine, for HPCG and graph, so we're only the third in HPCG and the second in graph, which in both of them, I think K computer is still the number one, which sort of shows their advantage in both memory and communication bandwidth. Okay, so after the comparison, you can pretty much get these major factors of this supercomputer when you want to map application onto this platform. Now, first, of course, this is actually the first supercomputer with a peak performance that is over 100 petaflops. So if you have some application needs this kind of power, you can come to us in Wuxi. And on our memory side, as I mentioned, for each node, we only have 32 gigabytes of memory, and the bandwidth is 136, not very good. If you compute the ratio of computing power to memory bandwidth, our number is roughly 22 flops per byte. This is actually a very high number. If you look at the most recent many-core architectures, right? Look at the Knights Landing Core, the number is somewhere around 6.5, and for P100 it's 7 point something. So you can see we are actually a very compute-hungry machine. I'll say we are pretty much bandwidth constrained in a lot of cases. Now, of course, we are also the first system with the kind of parallelism, with 10 million cores in just one system, with different kinds of cores, especially for the CPEs. As I have mentioned, we have different features. So we don't have, one thing I want to mention here is that we don't have L1 cache for the CPEs. Instead, we have a 64 kilobytes local data memory that needs to be controlled by itself. And also there's this register communication feature I mentioned earlier, which can support very efficient data sharing among these different CPEs. So, of course, when you want to write an application on this kind of supercomputer, the first challenge is about how do you scale? How can you design your parallelization scheme so that you can use all these 10 million different cores? And the second challenge is, of course, the memory constraint. We are not very good at this part, okay? We are not having a very good bandwidth as K computer does. But this can be, as I explained later, can be in many cases resolved, or say at least alleviated, by using these two different features of our CPEs. By using the local data memory, the fast docker, and also the data sharing among the CPEs to achieve a good efficiency. But of course, if you want to get there, along the way you need to spend a lot of efforts on refactoring and redesigning your application, your algorithm, and even your implementation of a lot of things. Okay, so that's about the machine. And now let me talk a little bit about the applications that we have on this machine. So first I want to talk about the programming model. It's kind of similar, pretty much the same as the thing that people are using on other heterogeneous supercomputers, MPI plus X. So the X can be Sunway OpenACC. It's a customized version of OpenACC that we use for the Sunway architecture. Or if you want some better performance and you can bear with some hard efforts, you can also choose to use Athread, where you can pretty much control all the computing and memory details and get much better performance. And also, sort of the general approach about scaling. In most of the applications, we are taking a two-level approach to map your computation onto the different levels of parallelism in your system. As I've mentioned, the first level is the MPI processes up to 160,000 MPI processes. And the second level, you have to remember you still have 65 cores. So actually the design challenge is that you have to reserve enough parallelism for this 65 cores within your core group. Or in many cases, as we see, you have to redesign your algorithm to expose enough parallelism for these 65 cores. The second part is about how you resolve the memory issues. So there are two things normally we have to do with applications, especially for golden bell price level applications that needs to use the entire machine. The first thing is you need to make really good utilization of your 64 kilobytes of local data memory. So instead of accessing the memory directly, you have to design a very good DMA scheme so that you can sort of overlap your data communication between the main memory and the RDM and your computing parts. So in this way, you can sort of hide all the latency. Now the second part is about data sharing. As I mentioned, we have this register communication scheme. Okay, if you don't use it, then it's wasted. So for a lot of the applications, you have to design a very nice scheme to actually share the data among the different cores, different threads within one core group at the register level. Okay, so now let me show you some concrete examples. So this one, I call it an incomplete list of full-scale applications. So basically, the applications that are capable of using the entire machine of Sunway TaihuLight, using over 10 million cores. So as you can see from the names, it's pretty much covered most of the traditional HPC domains that we are looking at. And for last year, we have these three applications that were selected as the Golden Bell finalists. So one is SOAR, or atmospheric dynamics, one is surface wave modeling, and one is a phase field simulation for material science. And of course, we were lucky enough to get China's first Golden Bell Prize with this implicit solver for atmospheric. So this year, we see some new things here. The first one is a graph processing framework. It's work done by Professor Chen from Tsinghua University and collaborating with Sogo, a website company in China. It's among the top 3 or top 4 internet companies in China. And also we see the traditional HPC applications. And again, we were very excited. So last week we got the news that 2 of these applications. So one is the CAM-SE, and the other one is the earthquake simulation work. They were again selected as the Golden Bell finalists of this year. So I'd like to show you some more details in these 3 applications to show how we actually achieve the parallelism at the level of 10 million cores, and also how we resolve the memory issues of this supercomputer platform. So the first work is the Golden Bell Prize winner of last year. Is an implicit solver. I think the major contribution of the work is in the algorithms. We have done a lot of work trying to use domain decomposition, multi-grid, and also customize the IRU algorithm to make it really efficient on this computer. So by doing that, we managed to get this implicit solver that was able to use all these 10 million cores of this system, achieving a sustained performance of roughly 8 petaflops in double precision. And if you are a climate guy, that translates into the simulation speed of 1 simulated year per day at the resolution of 3 kilometers, which I think is pretty good. And again, we were lucky enough to get the prize. So again, in this work, the first part is about how to map your computation among all these 10 million cores. So at the first level, it's still handled by the MPI processes. And I have mentioned in the beginning, you have to keep in mind, you have to reserve some computation, some parallel computation for the 65 cores afterwards. So in our work, we're actually using a very shallow multi-grid. So not like 7 layers, 8 layers. We only have 3 different layers. And we have this uniform decomposition, domain decomposition scheme. So we actually have a domain that can be easily used by the core group to get good parallelism in both computation and in data. So that's the first part of the problem. Of course, the second part of the problem is that we need to find a subdomain solver that can, solve the rest parts. So in this part, we have different kernels. Of course, we have different kernels to compute for the within the core group. But the most difficult one is the IRU. As you can imagine, IRU is not very parallelism friendly. So in our work, we were trying to design an IRU that needs only one single sweep. It's synchronization free and it also has improved data locality. So this is sort of our final design. It's a kind of 2 levels of different pipelines. So the first pipeline is along the z-axis. We have each CPE is wrapped to process through this pencil. And then along the x and y plane, we basically just start the thread in the corner first. And all the other threads, when they have enough data to process, they will start the computing process. In this way, we avoid the global synchronization for this problem. So by doing this, we were managing to using all these 10 million cores. And as you can see here, for 2 kilometer resolution, our parallelism efficiency is around 67%, and 3 kilometer is somewhere around 45%. So this one is the work, also an implicit solver on Sequoia homogeneous machine, 1.5 million cores, and the parallel efficiency is 33. So as you can see, this is pretty good results for implicit solvers. And this is the performance we get. As I mentioned, for weak scaling, we get 8 petaflops for implicit solvers. And for explicit solvers, we get 23.6. Now the actual performance, if you compare the simulation speed of these 2 approaches, so this again I think is a major contribution of our work last year, is that we performed this kind of comparison between the explicit and implicit solver at the scale of 10 million cores. And because the implicit solver, they can use a much bigger time scale, so the actual speed for simulation, the implicit solver is roughly 90 times faster than the explicit solver. So this is the first application I want to share. The second one is kind of different. This is our sorry for that. It's our MSE work that was selected finalist of this year. 30 people, around 30 people to work on this, and maybe around 15 to 20 people working on CAM. And some of them are working on the dynamic parts, some of them are working on the physics parts. So the outcome is that at the end of this project, we only have 2 students who are still willing to work on climbing codes. The other ones, as you can guess, they all move to things like deep learning. But you can understand, I mean, if you work on some code and you can't really read or understand them, it's kind of frustrating. So, again, this goal was actually achieved in 2 steps. The first step, we apply OpenACC to trying to refactor CAM. As I mentioned, CAM is divided into 2 major parts, the dynamic parts and the physics parts. So the dynamic part is the part that requires communication among different NPM processes, and it's luckily enough, it's usually written by computer scientists. So it's kind of easy to read. So for this part, we actually perform some manual transformation of the loops, manual optimization, and then we add the OpenACC to get performance. For the physics parts are the part I mentioned, written by many different research groups all over the world. And you can't really understand the code. So for this part, we have to rely on some automatic tools that can perform this kind of loop transformations, trying to expose the right size of both memory footprints and also computation to the core group. So that's for the physics parts. And this is the results we get after applying OpenACC refactoring. As you can see, we can scale to up to 24,000 MPI processes. That's roughly 1.5 million cores. But that's pretty much the maximum performance we can get by using OpenACC. The simulation speed is 2.8 years per day, is kind of competitive to the speed of N-Cars model running on Yellowstone. So as you can see, it's not very big performance improvements. So after doing that, we're trying to see if we can go further, if we can go beyond that. So in the second step, we were trying to apply an Athread-based fine-grained redesign of this dynamic core of CAM. So we actually did a lot of work. We rewrite the Fortran OpenACC to Athread C code so that we can get finer memory control. You know, the DMA operations I've mentioned in the very beginning, and also we can get much more efficient vectorization. And the second part is to use this register communication feature I've mentioned. You actually have to redesign your algorithm. So this is quite common computing pattern in CAM. You have to accumulate all these values along this column. And to do this using this 65 CPEs, you actually 64 CPEs, you actually need to redesign this in a hierarchical approach so that you can actually remove the data dependency and you can expose more parallelism to these 64 cores. So this is the results we have got, and as you can see here, the first one, the standardized one, is the performance of one single intercore. The second one is the performance of one MP. So just after we port the code onto Sunway TaihuLight. The third is the OpenACC refactored version. And the last one is Athread redesign. So as you can see, at the different stages, one Sunway core group, which has 64 or say 65 cores, their performance can be equivalent to 1/10 of an intercore, or 1.8 of an intercore. Or after Athread, it can be 7 intercores, or in the best cases, like in the vertical remapping, we can get the performance of roughly 43 intercores. This, I think, is pretty good results because the original code was written for Intel, not for this new architecture. And this is the results we get for scaling. We were able to actually scale the model to 8 million cores with a performance of 1.6 petaflops. The last one I want to share here is about the earthquake simulation work. Again, the highlight here is, although we have only one third bandwidth when compared with Titan, the GPUs. We can achieve the same kind of efficiency, and we were able to perform 10 Hz nonlinear simulation. Again, the first part is the parallelization. We designed this 3-level domain decomposition to achieve very good parallelism at the CPE level. I'm running a little bit late here, so I'll just go quickly. And also, this part about how you can reduce the memory requirements. We do array fusion to improve the efficiency of DMA instructions, and also we do register communication for the halo exchange. So after doing all this, as you can see, these are the speedups when we compare 64 cores with 1 cores. And this is the final results we get. 15 petaflops on Sunway TaihuLight. And if you look at all these numbers for flops, we are getting 12% of the peak memory size, 92% memory bandwidth, 73%. And for the fast buffer, we are using 93%. So it's pretty much pushing all the limits of this machine. And as I mentioned, we are getting slightly better, or say similar efficiency as Titan, even though we don't have a very good bandwidth. So the last part, the long-term plan of this machine. The first is, of course, for the traditional HPC applications, we want to convert science into service. This is not just some big words we want to say, because different from the supercomputers in US, I'm not sure in Europe, but in China, we have to find the money to pay for the electricity. So this is really, we want to keep the machine going on. And deep learning, we were doing something called Sunway DNA. That's a deep learning library for the deterrent instructions. And we also have a Sunway Cafe to support large-scale training. So here, sorry for that. As you can see here, the current results for AlexNet, this is not very large scale yet. We are still working on that. You can see that each core group is equivalent to 3.5 times of 24 Intel cores. Again, I think that's pretty good results. And also, Sunway Micro, which announced at this conference. So if you want to play with this processor, it's going to be available on the market pretty soon. Okay, so acknowledgements. Ministry of Science and Technology in China, they sponsored all these projects. And RCPC, the winner of the machine, they really made a very good supercomputer. And I also want to thank the friends from NCAR and also from SCAC, who helped a lot on our work on CAM and also the earthquake, especially Dr. Yifeng Cui. I think he actually started our efforts on this front. Okay, so that's all of my talk today. Thank you very much.